Thank you, Shay. Thanks for the invitation to speak in the Logic Supergroup. In fact, I was terrified because the speakers and the talks have been at such an excellent level. I mentioned that to Shay, but then he convinced me to speak anyway. So today I'm going to talk about the Muchnik topos. It's been a while since I have worked on this. This is coming straight out of my PhD thesis that I did under Professor Steve Simpson at Penn State. So anyway, so the story begins with, so here's the scheme, first of all. So I'm going to talk about a little bit about intuitionism, calculus of problems, Turing degrees. So everybody knows about this, but it's an integral part of the story, and hence I'll just bore everyone with these little things. So anyway, so here's the introduction. Intuitionism, as we know, is a constructive approach to mathematics that was introduced by Brouwer in the 1900s. Brouwer's work was continued by Heiting, and he gave a formalization for intuitionistic logic and arithmetic, and gave a natural semantics for it in a series of articles. So this we have come to know as the proof interpretation. There was another interpretation that was given by Kolmogorov in 1932. So this was in the abstract that I sent out earlier. It was mentioned as 1923. Shay has kindly fixed the abstract, which I saw this morning. So it's all good. So no error occurred ever. Anyway, so this was called the calculus of problems. And this was for intuitionistic propositional logic. So both the proof interpretation and the calculus of problems, they kind of merged at some point, and people started talking about the BHK interpretation. But anyway, so there were some interesting differences between the proof interpretation and the calculus of problems. Our work here is starting from the calculus of problems, not the proof interpretation. So here is the calculus of problems again. So in this informal interpretation, each proposition is regarded as a problem. The meanings of logically compound assertions are more complicated problems. So here are some of these the ways in which we interpret the propositional connectives. So suppose A and B are problems. A and B is the problem of solving both problem A and B. A or B is interpreted in the obvious way. Implies the implication is interesting, is the problem of solving the problem B provided a solution to problem A is given. So we are essentially reducing the solution of problem B to the solution of problem A. And we will see how this connects with with computability theory later on in the talk. And not A is the problem of deducing a contradiction from the solution of problem A. So then there's just a slide on Turing degrees, as I'm going to use these. So recursion theory started off as another constructive approach to mathematics, although I mean, it has become classical mathematics over the last, I mean, century or so. So here's the definition of Turing reducibility. So if you take two elements of the Baire space, we say that F is Turing reducible to G. If F is G computable, so if there is an oracle machine program that computes F using G as an oracle, so we denote this as less equal to sub T. So F less equal to sub T G will denote that F is Turing reducible to G. And there is the concept of Turing equivalence. So if two elements are mutually reducible to each other, then they are Turing equivalent. This is an equivalence relation on the Baire space, and the Turing degrees are the equivalence classes. And then the set of all Turing degrees is denoted by dt. And we can partially order dt as using the Turing reducibility relation again. Okay. Then we come into this these mass problems, which were introduced by Medvedev in 1955, to kind of give a formalized approach to Kolmogorov's calculus of problems. Kolmogorov never mentioned what he meant by problems. He said that as mathematicians, you ought to understand what is a problem. So anyway, so he also introduced a reducibility notion. This he called the strong reducibility, and now people generally refer to it as Medvedev reducibility as well. In '63, Muchnik came around and gave another reducibility notion for these mass problems. So this is known as the weak reducibility or Muchnik reducibility. And this is what we are going to focus on for this talk. In fact, this work is completely based on the Muchnik reducibility and not the Medvedev. So first of all, the definition. So a mass problem is just a set of elements from the bare space. So why is it called a problem? So a problem is in fact finding an element in that subset P of the bare space. So the solutions, the elements of the set are the solutions of the problem. So in that sense, you can say that the problem is identified with its set of solutions. So now we have the definition of Muchnik reducibility between mass problems. So suppose P and Q are mass problems, and we say that P is weakly reducible to Q if each element of G of Q computes an element or can compute an element F from P. So for each G in Q, there exists an F in P such that F is Turing reducible to G. And this is denoted by P is weakly reducible to Q. If you do this uniformly, then you get the Medvedev reducibility. So P is said to be a weakly equivalent or Muchnik equivalent if P and Q are mutually reducible to each other. It's much like the Turing degrees or the Turing equivalence. And this we denote as P is weakly equivalent to Q. This is again an equivalence relation, but now we have it on the power set of the bare space. The weak degrees are, or the Muchnik degrees, are the equivalence classes. And we can similarly, just like in the case of Turing degrees, we can partially order the set of weak degrees, which we denote by dW, using the weak reducibility itself. Okay, so there is a connection between dt and dw, of course, and that's why this talk is titled the Muchnik topos, which we will get to in a bit. So we consider the upwardly closed subsets of the Turing degrees. So the definition of upwardly closed is as usual. So anything which is above, if a point is in an upwardly closed set, then anything above it is also in the set. So we denote the set of upwardly closed subsets of dt, that is the set of Turing degrees, by this u dt. And then we can partially order u dt by the subset relation. And this you can do for any poset. So this is nothing special to the Turing degrees that we are doing here. And we can say that u is less equal to v if and only if u is a subset of v. So this is the partial order. It can be easily shown that udt is a complete and completely distributive lattice using the fact that dt is a poset. Again, nothing special for the Turing degrees here. Now the posets dw, that is the poset of weak degrees, and the set of upwardly closed, or the poset of upwardly closed subsets of Turing degrees, they are dually isomorphic. There is an order reversing bijection, which we are calling psi. So it takes upwardly closed subset of Turing degrees and maps it to the Muchnik degree of the set of the Muchnik degree of the set of functions or the set of elements of the bare space whose Turing degrees are U. And then finally, the connection with intuitionistic logic shows up here. DW, the set of weak degrees, is a Brouwer algebra. So DW is a complete and completely distributive lattice by because it's there is an order reversing isomorphism between DW and UDT. And UDT, we already said, is a complete and completely distributive lattice. So we just have to be careful about this order reversal, and then we'll be able to see that this DW is in fact a Brouwer algebra. So the supremum and the infimum, as you can see here, there is this is because of the order reversal. We have supremum defined in terms of intersection and infimum defined in terms of the union. The top element in DW is the image of the empty set. The empty set is the completely unsolvable problem. And this we denote that the weak degree of this is denoted by this infinity symbol. And the bottom element of DW is 0. And this is the image of the complete set of Turing degrees. Now, moreover, for any weak degrees, AB, there exists a smallest C star in DW in the class of weak degrees C, such that you have supremum AC is greater or equal to B. This is where it becomes the implication in intuitionistic logic. So C star is infimum of all C's such that supremum of AC is greater or equal to B. And we denote this C star by imp AB. Okay, so now finally DW as a model for IPC, which is intuitionistic propositional calculus. So we can now interpret propositions AB as weak degrees. So these are the interpretation brackets. So interpretation of A is a weak degree A. Sorry, this A should, am I using the same A? Yes. So this is interpreted as the weak degree A, and the proposition B is interpreted as the weak degree B. Then the propositional connectives can be seen like this. So again, we have to be careful about the order reversal. So A or B is interpreted as the infimum of AB. A and B is interpreted as the supremum of AB. And this is implication. Not is imp A infinity. So moreover, we have DW validates A implies B if and only if A is the weak degree A is greater or equal to the weak degree B. And DW satisfies A if and only if A is equal to 0. So this is kind of a I mean, we just wanted to show that DW is a Brouwer algebra. It's a model for IPC. Alternatively, we could have interpreted a proposition as an upwardly closed subset of DT. And then these would turn out as usual, like the interpretation would be the union and intersection and so on. Okay, so then we have just a slide or two about intuitionistic higher order logic. So this we are calling IHOL. This is a system of higher order intuitionistic logic or intuitionistic higher order logic that uses a many sorted language. Of sorts, there are some basic sorts, then product sorts, function sorts, power sorts, whatever you need to do mathematics. A countably infinite supply of variables for each sort, an equality predicate for each sort. Then this is for the belongs to relation. So for epsilon sigma for each sort sigma. Then an existence predicate, E sigma for each sort. So we are doing the higher intuitionistic higher order logic with an existence predicate. So we need to include this in our language. And we have propositional connectives and quantifiers. Okay, so then terms, formulas, sentences are as usual. We just have to be careful about the sorts. So for example, the atomic formulas are T1 equals T2. We just have to use the correct equality, the equality of the correct sort when T1, T2 are terms of some sort, sigma. And we have T1, I'm just going to call it belongs to, it's just easier. So T1 belongs to of sort sigma, T2, where T1 is of some sort sigma, and T2 is of some sort P sigma. And we have the existence predicate on S, and where S is a term, where this is of sort sigma. Okay, then so I mean we can generate the other formulas as usual from here, and then we come to Sheaves. Um, so I'm going to start with an example of a sheaf instead of giving a definition. So let's say T is a topological space. We are going to describe sheaves over the topological space T. So we take T and X as spaces, and omega be the collection of open subsets of T. Then the set of all partial continuous functions from T into X. So we have the collection of all functions from open subsets of T into X, such that A is continuous. This is the collection COTX with two operators. One is denoted by E, which takes an element from COTX and maps it to an open subset of T. And there is this restriction operator, which takes an element from COTX and an element and an open subset of T and maps it to another element of COTX. So E of A is called the extent of A. So it is just defined as the domain of A. So the idea is that a function is defined to the extent of its domain. And A restricted to U is just the restriction of A to U. So A is a function, remember, because it's an element of COTX. And you take any other open subset of T, you just do the normal function restriction. So this is the res operator that we have here, and this is the normal function restriction, up harpoon left and up harpoon right. So this forms a sheaf of sets over the topological space T. Now some properties that we can notice, or some of these characteristics that we can notice from this example are, for example, if you take an element from COTX, then if you restrict it to its own extent, you get that element back. Okay. So for any, then next is for any element of COTX, and if you take two open subsets of T, then you first restrict it to U and then to V, you are actually restricting it to the intersection of U and V. Then COTX can be partially ordered by letting, for AB in COTX, A is less equal to B if A is the restriction of B to the extent of A. And AB belongs to COTX. These two elements will be called compatible if they agree on their common extent. So A restricted to the extent of B is B restricted to the extent of A. So if they just agree on the intersection of their domains, then you can see that any compatible subset of COTX has a supremum in COTX. Now, if you just replace all these COTXs with a general sheaf, which will be just a set with two operators, defined just like in this case over here. So you just have to define E from the set M to omega, and the rest operator will be M cross omega to M. And then this will give you the definition of a general sheaf over the topological space T. Okay. Now, some more examples of sheaves. Instead of taking partial continuous functions from t into x, if you take the locally constant functions, so you take the functions from some open subset of t into x, and such that a is locally constant with e and res as in COTX, then this is again a sheaf. Here's a non-example of a sheaf, which is sometimes helpful, and also we'll come back to this later in the talk. So instead of taking the locally constant ones, if you take the constant functions from open subsets of t into x, then it is not a sheaf in general. So it's easy to cook up an example. So suppose you take t as r, x as r, and you take the constant function -1 on the half open, on the open interval -infinity to 0, and the constant function 1 on the open interval 0 to infinity, then these are both constant functions on open subsets, and hence these are members here. They are compatible because their domains are disjoint. If you glue them together, you get not a constant function, but a locally constant function. So therefore, the constant functions in general do not form a sheaf over T. We'll get to an example where they do form a sheaf, but that's later in the talk. Now, to set down some definitions. So suppose T is a fixed topological space. We define SH of T to be the collection of all sheaves over T. We can define sheaf morphisms in the most obvious way. So if you take M and N as sheaves over the same topological space T, just take a map which respects the extent and the restriction, and you have a sheaf morphism. Now, for sheaves over a space T, we can also define product sheaves, restriction sheaves, function sheaves, power sheaves, and subsheaves. All these together, the sheaves over a topological space T and the sheaf morphisms between them form a category, and in fact a topos. So this is the only reference that we have, or the only point where we refer to a topos. The rest is just non-category theoretical. Okay, so now the task is to see SH of T as a model for intuitionistic higher order logic. So for each sort sigma is interpreted as, so we fix a topological space T, and we take SH of T, the collection of all sheaves over T. And each sort is interpreted as a sheaf M. We are going to denote it by M sub sigma in SH of T, such that the sheaves for product sorts, function sorts, and power sorts are the corresponding product sheaves, function sheaves, and power sheaves. For each sort sigma and for each section that is a member of the sheaf, M sigma, we extend the language with a constant symbol for it so that we can later on go into important proofs. For each closed term S of sort sigma, there is a section, the interpretation square bracket S of the sheaf M sub sigma. So closed terms are interpreted as sections of sheaves. And then each sentence A is assigned a truth value, square bracket A, for the sentence A. So this will be an open subset of T. So the truth values are open subsets of T. So a few examples are as follows. So if S and T are closed terms of the same sort, then the interpretation of S equals T is the largest open subset of T, such that it is contained inside the intersection of the extents of these. So remember, these square bracket S and square bracket T, they are now sections of sheaves. So they do have extents, and you can take the intersections. The extents are open subsets. And S the square bracket S restricted to U agrees on this. So you take the largest open, which is contained inside the extents of both, and square bracket S restricted to this open U is equal to the square bracket T restricted to U. If S is a closed term, then the meaning of the existence predicate followed by S, that is, we want to say that S exists in some way. So the interpretation of this is really the interpretation of S equals S. So square bracket ES is the square bracket S equals S, and it gets interpreted as the extent of S from the previous definition of equality. I mean, the interpretation of equality. So if A and B are sentences, then we can see that A implies B is interpreted as the whole set, the whole space T minus the interpretation of A union the square bracket B, and you have to take this interior because you have to land in an open set again. If this is what we do in a topological interpretation for IPC as well. Now, if X is a variable of sort sigma and M sigma is a sheaf corresponding to sort sigma, then there exists XAX is interpreted as the union of all overall sections of M sigma of EA intersect A for X. So in other words, you just make sure that you are within the extent of A before taking this union. And if you want to interpret the universal quantifier, you will have to take the intersection, and there will be an implication, and finally an interior at the end. Okay. So we now come to a special case, sheaves over a poset. So suppose K is a partially ordered set, then it is, I mean, it's known that this forms a topology, I mean, the upwardly closed subsets of K form a topology on K, and this is in fact called the Alexandrov topology on K. SH of K is then the collection of all sheaves over the poset K, considered as a topological space with the corresponding Alexandrov topology on it. SH of K is obviously a special case of SHT, but it can also be seen as an extension of the cryptosemantics to intuitionistic hierarchy logic. Okay, so then we can do mathematics inside this sheaf models. So first of all, the number systems. So the natural number system is represented by a sheaf. So every number system will be represented by a sheaf inside SH of T. So as COTN, if you take the collection of all partial continuous functions from T into N, this is actually equal to COLCT, and that is the locally constant one, because any continuous function that you take from an open subset of T into N will be locally constant, because you have a discrete topology on N. So this is true for any topological space. We denote this sheaf by N hat SH. So this is the representation of the natural numbers as a sheaf inside SH of T. Then the fun thing happens in intuitionistic logic. The Dedekind and the Cauchy reals sometimes are not the same inside a model for intuitionistic logic, or intuitionistically speaking, the Dedekind and the Cauchy reals can diverge. So here we see that if you take COTR, so just replace, so if you take the partial continuous functions from open subsets of T into R, this is always a sheaf representation of the Dedekind reals, regardless of the topological space T. But for the Cauchy reals, if your space T is locally connected, then the locally constant functions from open subsets of T into R correspond to the Cauchy reals. So we denote these by RD and RC respectively. So for the non-locally connected spaces, this can be a little different. So I have a few examples here. But before that, we need to talk about the axiom of countable choice. Now, the axiom of choice in general is not accepted by intuitionists. I mean, it's obviously constructively problematic. But the axiom of countable choice is sometimes accepted. So the axiom of countable choice can be written like this, where X is a variable of sort n hat sh, which means we are really going to now drop the distinction between sorts and their corresponding sheaves. So that's why this is written as sort n hat sh. This is actually meaning that the sort which is mapped to n hat sh. Anyway, so X is a variable of sort n hat sh, Y is a variable of some sort sigma, and Z is a variable of sort n hat sh arrow sigma, which means it's a function sort. So Z is a function sort here. Now, if T is any topological space, RC and RD, that is the Cauchy and the Dedekind reals, coincide in SH of T. If this AC0, that is the axiom of countable choice, is satisfied by SH of T. Now, if T is locally connected, then SH of T satisfies the axiom of countable choice. Then we see that COTR, which is the representation of the Dedekind reals, must be equal to COLCTR. That is the interpretation of the Cauchy reals. Now, this is the interpretation of the Cauchy reals because we have a locally connected space here. And they have to coincide because RC is RD whenever SH of T satisfies the axiom of countable choice. Okay, so now some examples. So if you change your underlying topological space, things can be different. So for example, if you take the set of reals or R as T, then SH of R does not satisfy the axiom of countable choice. But RD is CO, I mean, this instead of COTR, we are writing CORR. And this is not obviously not equal to COLCRR because there are continuous functions which are not locally constant. And so RD and RC are different in SH of R. On the other hand, if you take the bare space as T, this is not locally connected, but it satisfies the SH of n to the n satisfies the axiom of countable choice. So in this case, RD and RC must coincide. So both of them are actually CO from the bare space to R, CONNR. So in both Cauchy and Dedekind reals are represented by the sheaf CONNR, n to the n R, and SH n to the n. Now, if you take a poset with the corresponding Alexandrov topology, it is locally connected and it satisfies the axiom of countable choice. So in this case also RD and RC must coincide, but in this case we have COKR is COLCKR because if you take a poset, then continuous functions on open subsets of K are actually locally constant. I mean, that is one way of proving this. Another way of proving this is in this case, RC must be, since it's locally connected, RC must be COLCKR and RD must be COKR and they must coincide. So therefore these two sheaves must be the same. Okay, now a more general axiom of choice in fact holds if you take X as a discrete topological space. Now this X can be possibly uncountable. So COTX is COLCTX. So this is just what we noticed earlier in when X was n, the set of natural numbers. If you take a discrete topological space for X, then any continuous function is locally constant. So so we have COTX equals COLCTX. And this is denoted by X hat SH, just like we denoted N hat SH for the sheaf representing the natural numbers. Then we have this more general axiom of choice, and this is satisfied in SH of the bare space and SH of any poset space. So this is just a generalization of the axiom of countable choice that we get in the sheaves over the bare space and the poset space. Finally, we come to the last leg of the story where we have the Muchnik topos. So here, this is the reason why we discussed Turing degrees and Muchnik degrees earlier in the talk. So the sheaves, so we have further specialized. So first we considered the sheaves over topological spaces, general topological spaces. Then we came to poset spaces. Now we take a very special poset, the poset of Turing degrees, and with the topology of upwardly closed subsets. So SH of DT is defined as the Muchnik topos. Now, why did we name this as the Muchnik topos? Because the set of truth values in SH of DT will be the open subsets of DT. The open subsets of DT are upwardly closed subsets of DT. And the poset of upwardly closed subsets of DT, in fact, the lattice of upwardly closed subsets of DT is isomorphic to the lattice of weak degrees via the order reversing isomorphism that we saw earlier, which we called psi. So hence, the truth values are really Muchnik degrees here, and hence the name, the Muchnik topos. Then in the Muchnik topos, we can interpret intuitionistic higher order logic. So for the propositional part, it stays pretty much the same. So psi of A is an element of the DW, psi of B, where A and B are sentences in IHOL. So psi of B is B in DW. So it will be, these will be just weak degrees. And then these are exactly the same as we saw before. And we see that SH of DT will satisfy A implies B if and only if the weak degree corresponding to, which is the interpretation of A, is greater or equal to the weak degree, which is the interpretation of B. So that is, if you go back in the order reverse, if you follow the order reversing isomorphism back to the open subsets, the upwardly closed subsets of DT, you will end up with the open subset that corresponding to A is a subset of the upwardly closed subset of DT, which is corresponding to B. And SH of DT satisfies B if and only if B is equal to 0. That is, if you remember that DT was mapped, the entire set of Turing degrees was mapped to the weak degree 0. So the upwardly closed subset corresponding to B, which is the interpretation of B, will be the entire DT in this case. That is the full topological space. So this is the connection. So this Muchnik topos SHDT, this gives a natural extension of Muchnik's DW interpretation. So the earlier interpretation of the intuitionistic propositional calculus into DW, that was done by Muchnik himself. So this is just an extension of the DW interpretation of intuitionistic propositional calculus to intuitionistic higher order logic. And finally, we have the axiom of countable choice and the real numbers. So it just follows from the fact that DT is a poset and that SH of K satisfies AC0, or the more general axiom of choice, where you have X as a set with discrete topology. So it follows from there that SH of DT will satisfy AC0, and in fact, the generalization of AC0. In the Muchnik topos, another thing happens. The Cauchy reals and the Dedekind reals, obviously they coincide because they coincide in SH of K for any poset K. Now, dt happens to be a directed poset. That is, any two elements of dt will have a least upper bound. And it turns out that here, any locally constant function is actually a constant function. So therefore, in this special case, the set of constant functions from open subsets of dt into R is a sheaf. And therefore, since else, here the locally constant functions or the continuous functions are already locally constant, and locally constant functions are constant, the Dedekind and the Cauchy reals are really represented by this sheaf of constant functions from open subsets of dt into R. So this is very special to directed posets and hence SH of dt. Okay, so things got a little bit less interesting in SH of dt because it's more fun to have various sets of real numbers. So we went ahead and we found some other real numbers in here. So these we called the Muchnik reals. So we can define a Turing degree of a real number via the Gödel numbering of rational numbers like this. So you take a rational number, we just assume that we have reduced it to these the simplest terms, and the Gödel number of this rational number is defined in this way. You can define it in other ways also. This is just one way. And then for any real number R, we define this subset of naturals like this. So it's the Gödel numbers, it's the collection of the Gödel numbers of all rationals such that they are less or equal to the real number chosen. And we take the characteristic function of this set. This is an element of the Cantor space, which is obviously contained inside the Baire space. The Turing degree of the real number R is then the Turing degree of the characteristic function chi R of this set NR. Okay, so we can define Turing degrees of reals, of course. I mean, this is a known fact. Now, within SH of dt, we can have a special class of real numbers based on this. The set of Muchnik reals, which we denote by Rn, these can be defined as the collection of all constant functions from open subsets of dt into R, such that the Turing degree of any element in the domain is above the Turing degree of the element in the range. So the range contains exactly one element here because this is a constant function. You take the Turing degree of that element, which is a real number, which is in the range of this A, and you take the cone above it. So that is, all these constant functions whose domain completely lies within the cone above its range, Turing cone above its range, is the collection of the Muchnik reals. Okay, so the Muchnik reals, so this definition can be stated like this. The Muchnik reals can be described as the set of constant functions from upwardly closed subsets of dt into R, that is open subsets of dt into R, such that the domain of each element lies within the Turing cone above its range. Just, as what I was trying to say earlier. Now, this class of Muchnik reals is interesting because the element seen as coming into existence in some sense. So as we move up on the partial ordering of Turing degrees, that is, as we get to know unsolvable problems with higher degrees of unsolvability, then these more and more of these real numbers come into existence. So it's kind of, it reminds us of the the creative subject of Brouwer. Although I haven't, I don't know whether, I mean, I don't know if this is the correct mapping of the concept of the creative subject. Um, the Dedekind and the Cauchy reals in SHDT is the collection of all constant functions from open subsets of DT into R. However, you cannot say that every constant function is, every such constant function is a Muchnik real. So the class of Muchnik reals is a proper subset of the Cauchy or the Dedekind reals in SH of DT. So, I mean, we proved a couple more properties of the Muchnik reals in the work, but I think I wanted to stop here. So that's it.